Hi, just me and a few of my friends here. We're going to talk about different ways to pass messages between. There's really a bit of feedback here. Different ways to pass messages between threads, different frameworks, different APIs you can use, and walk through different frameworks that are available right now. Before we start, I'm Nitsan Wakart. I blog. Don't know if any of you read the blog, but thank you. It's sort of okay, popular, I don't know. And I do some open source work, mostly JC tools, which we'll talk about. I did a bit of work on Aaron and Agrona, which we'll also mention, and a little bit of work on different sort of projects. It's, once you start, it sort of becomes a habit, which is very nice. And also, I'm the organizer for the Cape Town Java user group. So if you're in Cape Town and you want to give a talk, come join us. Then it's quite nice down there. I work on Zing. Zing is the best JVM available out there because I work on it. Only works where it's important to work, which is the Linux platform and x86 machines, so Intel. Server-side systems, obviously, with those requirements. So if you're running Cassandra, you're running web servers, you're running your applications, whatever it is you run on your servers, where the JVM you should be using. And we're focused on responsiveness. We have a completely concurrent GC algorithm, so pauses on the scale of sub-milliseconds. And we have Ready Now, which is a way for the JVM to persist your profile data. So when you when you restart your application, all of that data is reloaded, and your application is start from the very beginning of the day. Finally, there's an amazing team. I've been with Azure for like 3 years now, and it's a pleasure and an honor to be amongst them. Eventually, they'll find out and fire me, but so far, it's been good. I just been to Monica's talk about the G1 GC, and I've been tuning Oracle GC recently, so I've decided to add this slide, which is just a little bit of heckling, but this is the complete guide to tuning GC on Zing. So you need to set the heap size, and that's it. You set the heap size, and it just fucking works, and there's just no need for all of those, extra, what happens if I'm a young GC? Yeah, none of that. So it's very, very simple, and with that simple configuration, you will get the sort of sub-millisecond GC pauses. So that's pretty much where it ends. I don't actually configure GC at all these days, so it's great. Before we get to queues, I'll just be clear, you don't always need to send work to other threads. So if you're going to scale your application and add threads, scalability comes at a cost, and concurrency is difficult and all that. So there's this quote about scalability on like clustering and so on. You can have a second computer once you know how to use the first one. And there's this one from Martin Thompson, which is, you can have another CPU once you figure out what the hell you're doing with one. These things hold, but we're not really going to touch on them. We're going to talk about message passing. Message passing has become sort of infrastructure for a lot of the frameworks people use these days. RxJava, all the reactive processing type actors and so on, all of those frameworks are built on queues on message passing between different threads or between different units of execution, if you will. So we're going to talk about some new features that you may not have realized you're missing from your queues, and about some new ideas. So maybe there's different ways to arrange your threading model that might prove useful. And you can take those ideas and feed them back into the way you think about concurrency. And finally, big show, jumping, so on. Right. This is how your average application threading model looks. It's like a noodle soup, different threads talking to all the other threads in different and exciting ways. And for our purposes, all these arrows are queues, but in a lot of applications, there's all sorts of other signals between threads, be it locks or semaphores or concurrent data structures for sharing information. For this presentation, we're only worried about queues, and the most typical use case you have is you have some incoming events, and you put some work on a queue to be executed on another thread or a thread pool, and those work items result in further work, or they result in calling back to some network layer thread, etc., etc. And yeah, very quickly these things become spaghetti soup, just like this one. The JDK gives us some excellent building blocks. I think one of the reasons concurrency has been so successful on the JVM is because those building blocks are part of the toolkit. So we have concurrent queues from JDK 5, we have executors, we have the fork join pool, and we have parallel streams with JDK 8. So all of that just comes out of the box, and we're not really going to touch on any of it because obviously you all know that. Why would we want more than that? And the reason people turn to other solutions are, manyfold, but I think good reasons are performance, which I'll expand on in a second, and features, which we'll sort of discuss in the context of each framework we'll be touching on. So the difficulties people have with performance on JDK queues is that in some cases they can't meet the latency requirements using the JDK queues. A lot of the times it's because of the synchronization mechanism between the producers and the consumers. It might be that people want higher throughput. Again, the JDK queues are great for a great many applications, but in certain domains you just want more. And on top of that, there's the whole lock-free queues have become like a big deal, or lock-free algorithms. There's some genuine issues with the terminology a lot of people use in that field, but people want a way to interact with data structures that is guaranteed to not block them and put their thread to sleep. And there's different levels of those guarantees, from just I'm not going to use locks to I'm going to be wait-free and in a fixed number of instructions, I'm going to give you control back. There's a whole range there, and the JDK offers a fairly limited selection in that area. There's the concurrent linked queue, which is the sort of one lock-free, lockless queue you can use. And finally, you probably want queues that are more GC friendly or less GC intensive. One of the misconceptions in the sort of queue area is that array blocking queue is backed by an array, and therefore there's no allocation involved when you use it, and that's actually not the case. The queue itself is backed by array, but the lock that it uses is there's a waiter linked list on that queue. So every time you wait on the queue, you add a node to the wait list, and then you take it off, and it generates quite a bit of garbage, actually. So we're going to start with queues because everybody's familiar with queues. This is what a queue looks like. You have a producer and you have a consumer. The consumer takes elements off, and the producer shovels more elements on. JC Tools is a library that I work on and a lot of other people contribute to, which is the pleasure of open source development. It's Apache 2 licensed, and you may not be aware that you're using it, but a lot of people do these days. It's used behind the scenes in Netty. It's now used in Cassandra for certain purposes. It's used in RxJava. So it's in a lot of places I didn't really think it would get to when I started working on it, but there you go. So at least in theory, it should work. It seems to work for some people. So have a go, enjoy it. We all know the queue interface. The queue interface in the JDK has a lot more methods than offer and pull. It's a collection, which means it's like a whole host of different bits of functionality have sort of seeped in. JC Tools is a fairly minimal sort of queue implementation in the sense that it's focused on message passing. So, if you want to iterate across the whole thing, it doesn't implement that. But what it does do, it does extremely well. And it also offers an extended queue interface, which offers two main sort of differing features. There's relaxed pull and offer, and that means the offer and pull on the queue interface conflate two concerns. When you offer, you get to know, you're guaranteed that if you fail to offer, the queue is full, and similarly on the pull side, you can take an element. If you don't get an element, it means the queue is empty, and it has to be empty. That in turn means that if you implement that queue, and it just so happens that when you pull, I don't have an element to give you because of the queue implementation, but the queue isn't empty either. I have to spin and wait for you to have visibility to the next element in the queue, and that may take any amount of time. So having a sort of relaxed guarantee on those methods allows me to implement further optimizations in my queues. which results in better performance, which is measurable. And the other two features are drain and fill, which are sort of batch operations on the queue. Drain, you might be familiar with from blocking queue, and fill is the other side of it. So you want to put 10 elements in a queue, you'd use the fill method, and the upside of having that functionality of declaratively saying, I'm going to put 10 elements in right now, is that you can reduce contention by upfront claiming chunks of the queue rather than claiming a slot at a time, which also can improve performance dramatically. It reduces contention on either side, etc., by claiming larger chunks. So this is what it looks like. It looks just like you'd think it does. So there's the relaxed offer, looks like the offer. There's the relaxed pour. And filling, filling comes in actually like 3 different flavors, but the important thing is you know that you want to put a lot of elements in, and you use the batch interface. So we have a slightly extended interface for the queue, and we have the queue interface. The big sort of conceptual change when you start using these queues is that they come in different flavors that are customized to your threading model. So if you know that you have a single producer, single consumer sort of relationship between 2 threads, you can have a queue that is customized to make the most of that opportunity. And similarly with multi-producer, single consumer, and the whole range is there. The JDK queues, because they have a wider sort of appeal, they have to be more generic. They're all multi-producer, multi-consumer. If that's your use case, if you don't know how many producers and consumers you have, you might want to go for the multi-producer, multi-consumer sort of queue. But in many other cases, an opportunity arises to use a more reduced synchronization mechanism. So one good example is anything to do with networking, any sort of resource that you're only allowed to use from one thread anyway. Logging is a good opportunity for sort of multi-producers feeding into a single writer into a file, etc. So just to clarify, which I'm sure you'll understand this, but when I say single producer, single consumer, there's one thread that produces, one thread that consumes. The producer is not allowed to consume unless they're both the same thread, which normally they're not, because if they are, what's the point of using a concurrent data structure? Some people get confused, most people don't. And then we have the multi-producer, single consumer case, which is lots of people shoveling in from one end and one guy reading from the other. The queues come in several sort of flavors, and this is where it gets more interesting. There's a circular buffer sort of flavored queue, which is the bounded queue or the array-backed queue, where you pre-allocate a buffer and you sort of go round and round. The consumer chases the producer, and they put elements in. The reason it's called a circular buffer is because when you get to the end of the array, you start back from the beginning. This is, the principle that's behind array dequeue, behind array blocking queue for that matter. Many other queues, included the disruptor, which we'll get to further. The one extra point to realize in this sort of diagram, we have values in one region of the queue, and the rest is nulls, the rest is empty. The values are not actually inside the queue. The references to the values are inside the queue. You put the reference in, and when you need to read it, you need to sort of go find the queue, read the reference, read through the reference to the values that you're actually looking to use. So there's a bit of indirection, which is pretty normal in the Java world, but this is how these data structures work. The other type of queues people might be familiar with is a sort of linked queue, where you have a node, you put the value reference in it, and the node references the next one, and the next one, and the next one. Linked queues are used in the sort of environment where you want to have an unbounded queue. The problem with them, however, is that they're quite GC heavy, because every time you read from them, you have a node you really don't have anything to do with anymore. So you throw it to the GC, and they build up, and then you come and collect them, which is not a problem if you're using Zing. But if you're not, then you're not. So where I found and sort of fixed a little bit the sort of these sort of queues, multi-producer, single consumer linked queues is both in Netty used to have one before they started to use the one from JC Tools, Akka, many other places, and they want an unbounded queue, and this is the only option the JDK has, and so they go for it. I've implemented in JC Tools something that is sort of novel, which is sort of linked array queues, which instead of allocating a node for every element, you allocate an array and you reuse that buffer as much as you can. But if you have more elements than that, you link to another buffer and so on and so forth. This means you're far more cache friendly, you're far more GC friendly, and you do a lot less, you generate a lot less garbage because you can stay within a buffer. If your producer doesn't outrun the consumer too much, you can actually be very safe. So some actor systems are sort of slowly moving in that direction. In particular, RxJava is using the single producer, single consumer flavor of this queue. So should you be using JC Tools? Yes. But I think more importantly, maybe you shouldn't be worried about queues. You need to figure out if queues are a bottleneck for your application, and is that where you should be spending your time? And if they are, you can consider that, but you need to start worrying about how many threads are putting data in, how many threads are reading out, etc. It's a bit of a mindset shift that you will need to accustom yourself to. The interface is very similar, so it's pretty much a drop-in replacement. I say pretty much because iterator isn't implemented because I don't consider it very important to the use case. The methods that consider it a collection are not complete. For most people, this is absolutely fine. I've had one complaint from a person who he needed the functionality because he was using it for testing, not actually in his relevant code as far as I know. So queues transfer event reference between threads. That means you take the reference, you write it in. At the end of it, you clear it out. It doesn't stay with the queue. You can take an event, you put it in the queue, you take it off the queue, you can put it in another queue. There's no problem with that. And that's the only thing that's shared. That's the thing you communicate between threads. I mention it because we're going to move on to data structures where that's not the case. There's issues when moving to this sort of way of working. One of the things that happen a lot, especially with executors, you allocate the runnable that you're going to put in the work pool, you throw it in, and at the other end, someone takes it out, runs it, and then throws it on the heap. So it doesn't matter that you're backed by an array because every time you put an event on, you allocate it, right? You can tune the GC to deal with this problem, or you can have some sort of object pooling solution. There's some simple things you can do, like you can have two queues, incoming objects, and then shovel them back out to the sender to read back and reuse. That's a scheme that works. It's pretty simple if all the objects are the same type. But if that's not the case, you can look at some existing sort of object pooling techniques. The other thing is, these are just queues. They're building blocks. I can't tell you how you want to chain your application up. You have to build on top of it, which is why JC Tools is often used by library writers, and I think some people use it directly in their applications, but that's perhaps infrastructure work is where you'll find the usage for this sort of thing. You'll have a queue to a thread pool to a queue, or a queue to a thread that has a particular task to another queue, but you'll have to take care of that yourself. It doesn't prescribe upfront what the relationships are. And the last thing is, people using the JDK often use blocking queue. There's no blocking queue at the moment as part of JC Tools, and blocking with sort of lock-free, wait-free, lockless algorithms requires that you come to your own conclusions on what to do when you're idle. And this is where the wait strategy comes in. Wait strategy as sort of a term I'm familiar with from the disruptor, where I've seen it for the first time. And a wait strategy answers that question of what should I do when I'm waiting for data to become available, or if I'm waiting to win a CAS, or if I'm waiting for anything that I don't have work to do, so what should I do while I wait for more work? There's several options, and you can sort of mix them. You can spin, you can just burn a call by while true, try to do something. With Java 9, there's on spin wait, which is a hint. It's a JEP that got in recently from Azul. Our guys sort of developed it, and a lot of back and forth with the community, and got in and should be available in JDK 9, and gives some very nice benefits because it hints the CPU, especially on Intels with the pause instruction, hints the CPU that you are spinning in anticipation of data appearing, you're not just burning resources, and it helps latency to become more predictable. It's been used now in the Java util concurrent classes, and there's some successful experiments with the disruptor, etc., using that as part of a wait strategy. You can use thread yield, which sort of gives a bit more room to other threads to execute. You could sleep for a very short period of time, so use lock support, park nanos, or you can all out park your thread and wait for somebody else to notify you. You can use a lock. It adds up to the same thing. Somebody else is going to come along and release you when data is ready. Using that sort of wait strategy ends up looking something like that. You have your queue. While the offer is failing, you're going to wait. Similarly, on the other side, while your poll returns null, you're going to wait. It's a small adjustment to make in your code. Wherever you have take or put, you now have a loop. Where it becomes sort of useful is that now you can choose to do something else. So you can poll, and if there's nothing there, you can check that the selector doesn't have any events ready for you on the network layer. You can check another queue for more work. You can pick your next item from somewhere else, perhaps. I'm going to do several stops for Q&A because there's sort of 3 distinct stages to this talk. So does anybody have any questions about JC tools or anything I've mentioned so far? Going once, going twice. All good. Let's move on. Next one along. The disruptor from LMAX. Anybody here using the disruptor in a production system to do something or another? Okay, excellent. The disruptor's been with us for like 6 years now, I think. Open source, again, it's developed by Martin, who's sitting there, and Mike, and Trisha, and good folks from LMAX. Trisha is probably where everybody else is. They're all watching Hair Talk. But yeah, used by many, many other people outside of LMAX, and well established. So yeah, it's a pretty solid choice, not something to worry about. Importantly, the disruptor is not a queue. I think initially when it came out, it was a step up from existing queues, but it wasn't a queue. People put it in there because they didn't have anything better to use at the time. I think nowadays there's other solutions available, but the disruptor is a lot of things. It's not just it's not intended to be used as a queue. What it is a single or many producers multicast to single or many readers. And what multicast means in that sense is that I can have several readers see the same value. Now, that's entirely not the case with a queue. With a queue, you poll a message, you're the only one who got that message. With the disruptor, you can have workers chained behind one another, or you can have them in parallel. If they're in parallel, they will see the same messages coming through. They won't interfere with each other. Readers can be ordered or parallel. You allocate all the events up front, and you put them in the queue. That means that you don't, or at least you shouldn't really be writing your event reference into the disruptor and then reading it out and nulling it, because that's what you do with a queue. If you write references into your events inside the disruptor, you're potentially setting yourself up for a memory leak. So it's the sort of thing you need to worry about. But the idea is that you know what sort of event you want, you fill it up, you hand it off to your consumers. There's some nice properties that come with this. One of them is that you have a lot less sort of mobility with your objects. They're allocated up front. They're probably moved to all together. You allocate them all in a tight loop, so they're very likely to be allocated next to each other, moved all together, and stay in nice chunks for the CPU to read through. So even though you go from the array to your object, they're actually like 2 different streams of memory you're reading into your CPU, so it should be very nice, very cache-friendly. There's pluggable wait strategies out of the box with the disruptor, and this is roughly what your application ends up looking like. As you see, all the values are in the queue, they stay in the disruptor, they stay in the disruptor. We can have thread A, which is the producer in this use case, writing events in. And we have 3 stage Bs, all happening in parallel. One of them is at the beginning of the area that it can access, and the other one is at the end. But they can work in parallel. They don't get in each other's way. Once all of them have finished reading events, the C processor can start working on them and move in that region, in that batch that's available to it to process. And when the C processor is done, the A producer can write over them again. So they gate each other using the sequence that is part of the API. So what does the API look like? You create a disruptor. You, importantly, you give it an event factory so it can allocate all your events up front. You give it a thread factory so it can place the consumers on different threads, and then you'll chain your consumers correctly. And you have a producer type. If it's a single producer, you'll use one strategy to write into the disruptor. If it's a multi-producer, you'll have to use another strategy. And then you have a wait strategy that will dictate how different people wait on each other within this disruptor. And once you've done that, you have a handy DSL to sort of write out the flow between your threads. What's also, again, different from a queue, with queues as building blocks, if I have a producer, a consumer, and then a third consumer downstream from the middle one, I need 2 queues. Now here, everything is on one sort of block, and I can just hand it off between them. So it's all sort of a production line type transition between the different threads. When you publish, this is what it looks like. You claim a slot, you claim the number of the slot, you get the event that you can write into from the ring buffer, and then you write into your event whatever it is that you want to write into it and publish the sequence. You don't write the event into the disruptor. Again, the disruptor holds the events at all times, and whatever it is that you put in, you need to release that sequence so other people can see it. You can also use the event translator. If it gets inlined, it's fine. If it doesn't get inlined, then you'll have a bit of an overhead to it when you publish events, but basically it just makes for a nicer sort of API to use because you don't need to worry about the sequence. All that boilerplate is done for you. You put your event, and the event you put in is copied from. You don't put that event into the disruptor. Again, just highlighting that. On the other side of the disruptor, you have your handlers which read the events from the disruptor. So you implement this interface of handling events. So on an event, you know which sequence you're at, and you know if it's the end of a batch of events. So when batches become visible, you can be notified when the recent visible batch has been sort of consumed. This is not the only way to process events off the disruptor. I personally, I think there's a slight problem with taking cues from the number of events that became visible, but this is the way it works. So this is the default batch processor code. I'm only showing it because I think it's nice to know how things work under the covers. You look out for what is the next available sequence number. It may not be the one you want. You want the next one. You want the next event. It might be that there's 100 events available into the ring buffer, and then you loop through all of them and you pass them into the event handler. And as you do that, you increment the next sequence. Next sequence is a local variable. No one knows that you've made progress during that batch. And at the end of it, you set the sequence. You notify everybody else that you're done with your batch. The problem, as I see it, is that nobody knows that you've made progress. If you read a really long batch and somebody else is waiting for some work, and you're delaying them from getting started on the beginning of the batch that you're already done with. You can use the disruptor in a way that works around this problem, but you need to be aware that out of the box, this is the way it works. So if you're using the disruptor to, say, write to disk, and while you're writing to disk, other people are waiting to also handle those events, you might want to consider using the non-default sort of batch processing. There's a different API that's currently experimental for event pooling. Looks a bit more like a queue than the disruptor currently does. And with it, you don't volunteer your threads up front. You can go to the disruptor and say, I'd like to handle some events now with my thread. Different APIs for different people. This is sort of perhaps an easier entry than using the full-out disruptor if you're currently using queues. LMAX used the disruptor, and it's important to understand their use case because they developed it for their own use case. And if your use case is similar, maybe you should consider it using. You should consider using it as well. But if your use case is wildly different, perhaps that's not the right tool for the job for you. Just because the technology is cool doesn't necessarily mean you should use it. They're using the UMS messaging framework, so a messaging product, which is reliable UDP. It used to be called LBM, which was a much better name. And this brings in messages from the network. Now, the UMS subscriber brings in messages. It takes the binary content and puts it into a byte buffer. And that's the event on the disruptor here. The disruptor carries byte buffers around. Okay? And the reason you might want to do that is because byte buffers are large sort of chunks of memory. You don't want to allocate them and throw them away the whole time. It would cause massive GC pains. You want to upfront allocate them and reuse them. And the disruptor allows you that sort of transmitting events and recycling them all in one go. Okay? The next stage is writing them to disk and replicating them to the sort of hot or the warm or backup server. If you're doing some sort of clustering solution, this again might be a good sort of use case for you. You can't process the event before other people saw it, before you wrote it to disk. So here we do the writing to disk in parallel to sending it to other people to see it. Only once both have finished their work do we join and go on to the next stage. If you think about doing this with queues, this is where queues become, insufficient as synchronization mechanisms. Okay, I want to do some work, and then I want someone downstream to see the work, and they would have to sort of merge streams from two streams upstream. It becomes really complicated. Or if not complicated, at least it's not something that queues do out of the box for you. The disruptor covers that really neatly. Once we're done with replicating and journaling, we move on to the business logic, and once we're done with the business logic, they have a second disruptor that they copy the outgoing message into, which is not in this picture because it's not part of the same disruptor usage. What is really neat here is that they leave the messages in the queue just in case they need to be replayed. So that's a nice property of the disruptor. You can leave some data behind and trim it as you go along, and it works really well for the messaging use case. So should you use it? It's very stable, tried and true. It's in production for many years now. It's a new API. It's a little bit of a sort of mindset change. It's a little bit of a code change, but these are not insurmountable sort of challenges. The things to worry about are there's only one event type in the disruptor. If that's a good fit for your use case, that's great. But if you're implementing a more sort of generic workflow where there's a lot of tasks that go into a work pool, and that work pool needs to deal with different types of tasks, you might need to consider how you can implement that using the disruptor. And another thing that is, I think, a common pitfall is that it's not a queue. You can't leave references lying around inside your events, otherwise you'll get a memory leak. So the disruptor, as opposed to a queue, the disruptor transfers the event lease between threads. It doesn't transfer the event. The event never leaves the disruptor. You get the event. Once you notified other people that you're done with it, you can't hold on to it. You can't take an event out of the disruptor, put it on a queue to be used somewhere else. That'll just blow up. There's a lot of material online. There's some great blog posts from the guys at LMAX. There's talks to watch if you want to learn more about it. In particular, the one I mentioned here from Mike is an excellent talk. So that's it on the disruptor. Do you guys have any questions about this part of the talk? Any questions about the disruptor going once, going twice? Moving on. Right, next one along, the Aaron IPC. It's the latest of the bunch. Version 1 has been released quite recently. This is another Martin Thompson production with Todd Montgomery. Todd used to work for Informatica, so he's behind the UMS messaging, which we just mentioned. And they both work with Richard, who's somewhere else, but is also a speaker in this conference, gave a talk yesterday about generics. And they all collaborated on the Aaron IPC. It's open source. The IPC is just a part of what Aaron does. Aaron is a reliable UDP transport, and the IPC is part of that framework. It's entirely, it's not a generic solution, But it is, I think, a reusable part for other frameworks, so it might be something you can use in your application for different things. The main client for Aaron is finance and hugely demanding environments. So again, if you don't fall into that category, that's fine. But if you do, this might be a lifesaver for you. Okay, so what is it? It's not a queue and it's not the disruptor. It's entirely off heap. It's a multi-producer, single consumer broadcast channel. It's not, again, you can have many readers looking at the data. They don't take data off and, somehow ensure only one person saw it. That's not their concern, okay? It's off heap, so you can't put references on it. If you're going to put your events in objects and then you want to put them into the Aaron IPC, you would have to serialize them on one end and take them out on the other end. Again, you're probably in the wrong place, okay? There's no reference passing. It is for cross-thread or process or language usage. So I can write my code in Java. I'll write my data into the IPC. On the other side, some other process in C++ or in C# will read that data, do something unbelievable with it, and move on with its life. You can also use it, though at the moment I don't know if anybody is using it for it. It should be a great fit for using in-process as a replacement to JNI. So if you want to talk to your JNI layer without going through JNI calls, which come at a high price, this might be a great solution for you. So it's sort of an async JNI layer. It's multicast, as I mentioned. It comes, so this is a full-featured IPC solution. So if you talk to another process, the other process may die. So you want to be able to detect dead publishers. So that's out-of-the-box functionality. And on top of that, if you've watched Martin's talk yesterday, he went into great detail about the algorithm. So either look that up online or go look at a code. It's a terrific algorithm and a very interesting read. And this is what the process looks like. You have a publisher or a few publishers. They might be in the same process in the same language. They might not be. Okay, you could have two publishers from two different processes writing into the IPC. You can have multiple subscribers, all of them reading from the log buffer as they go along, and they don't get in each other's way. Once all of them have sort of cleared their way through it, the publisher is free to come back and overwrite the data again. So it's a bounded transport, but there's a mechanism in place to allow several subscribers, not just one. And performance is great, but we're not really touching on performance here. The API looks like this. You create a publication, and then you offer a byte buffer in. In this usage of the API, Aaron will copy out your data. So you offer a direct buffer. This is not the Java direct buffer. It's part of a Grona. It's a wrapper around either a direct byte buffer or a heap byte buffer, but it allows more efficient usage. And the data in that buffer will get copied into the log buffer at the with the offset and the length are the offset and the length inside the buffer, so you can reuse it, etc. And you get a result which indicates if it was successful or why it wasn't successful. The subscriber API is, again, it talks about fragments because this is geared towards a messaging system, and a message might be spread across several fragments. So you implement a fragment handler. If your messages are small enough, they will never occupy more than one fragment, so it's not something you should worry about. So when you get a fragment, again, you get handed a direct buffer with an offset and a length and a header. The key here is that on the consumer side, there's no copy. You're getting effectively a lease on the data that Aaron is seeing, and when you're done with it, Aaron is going to take it back, but it doesn't copy it out for you. Okay? If you want to do that, you can do that, but that's not what it does. And as a note here, you can see that the polling interface calls out its own batching. It says, I want 10 messages, I want 100 messages. At the end of it, I want my control back because I'm going to do something about it. It doesn't rely on the visibility in the buffer to dictate the size of a batch. So it doesn't have the same risk of running through however many events before reaching the end of batch event that will do something. The publisher also have a zero copy API, which is similar, if you'll notice, to how the disruptor was working. We claim a slot, and then when we've claimed successfully, we move on to writing into the buffer starting at the offsets that we got back. When we're done, we commit the buffer that we got. Okay? We didn't copy the memory out. Sorry, we're trying to avoid copying the memory in and not copying the memory out. So we got a chunk of memory. We can use that, and when we're done, we commit what we wrote into it. The Aaron APC, and I don't know how well you can see the different arrows. All the black arrows on this diagram are the Aaron IPC. So it's used all over the Aaron transport layer. It's used to communicate between the media driver to the subscribers and the publishers and so on and so forth. And it can also be the media between two processes. So this is where it fits in as part of the Aaron story. And what this does is offer a really clean and efficient sort of fusion between your messaging layer and your subscribers. So think of it as a step forward from the disruptor, where the disruptor managed the byte buffers, but the messaging was done by somebody else. So they had to rely on the somebody else thread model and somebody else's sort of formats, and they only got the messages after so long. Here, Aaron is taking care of everything. So as a result of that, the format on the IPC is very similar, or exactly the same, in fact, as the format on the wire. So messages are copied in, and when you want to send them, they're taken out and sent along. So this results it results in great performance for Aaron. It also means that you're paying perhaps fractional, but you're still paying a slight overhead for the fit that this is for Aaron. So it's a great solution. If you are somehow not satisfied and you want to go further than that, you could strip parts out and make it go even faster than that. But I don't think so far the use case have come up for it. So should you use it? Now that version 1 is out and some people have been using it in production for a while, I would say it's pretty stable. It's still sort of cutting edge. Not that many people are using it, but if you need it, like I said, it might be just the thing to help you make your targets. Really helpful if you need cross-language, cross-process message passing. There's not that much available in that space. And finally, if you need to broadcast to multiple subscribers, which is a great feature in certain domains, it's on the table here. Just repeating here, the event contents are leased between threads. They're not necessarily copied out, not necessarily copied in. You hire a slot. When you're done writing to it, you release it into the buffer. You lease the slot. You read, and when you're done with it, it's it. You can't take it with you. It's and the result is you don't need to worry about copies everywhere. Any questions about Aaron, with the benefit that if I get it wrong, Martin can correct me on the spot. Questions about Aaron going once, going twice? Nothing. I don't know how much time we have. We have 10 more minutes. I usually run over my slot, so I cut it a bit short, but there's further material. Before I go into it, just a summary of where each one fits. So if you need faster queues and you need the queue interface, deliver once, and you want to have a minimal sort of transition to just faster queues, use JC tools. If you have this sort of use case where you need to chain your consumers, you want to multicast events to several stages in your pipeline, Disruptor is a great fit. Also, if you want to solve your object pooling while you're at it, the Disruptor might be just the thing for you. And finally, if you're trying to shift binary data between threads or between processes, Aaron is probably your best choice. The other benefit of Aaron, which I haven't sort of pointed out in the slides, but with queues and with the Disruptor, the values are somewhere else. You have the reference array, and then the actual data, the actual values are somewhere else. And it's down to the mercy of the GC where to put them, and they happen to end up well on the Disruptor, and they could end up anywhere with queues because I don't know where they came from and when they get collected, etc. With Aaron, the data is in the queue. It's inlined to your stream of information. There's two benefits to this. One is that there's no need to do any dereferencing, and the other one is that, sorry, what was the other one? It's very cache friendly, there's no dereferencing. There was something else, but it'll come to me later probably. Prefetching. No, there was something else. Yeah, no, let it be prefetching, yeah. I'll curse myself the whole day about this. Fine. Right, we're up to bonus material. Does anybody have any questions up at this point? So this is not strictly the how is Aaron implemented talk, but so how is the networking layer implemented in Aaron? They use NIO at the moment, so they have their own. It's sort of similar to Netty's event loop around a selector with some extra enhancements, and from that point onwards, UDP sockets. Right? There's no magic there at the moment. There is talk of implementing a native layer which would enable a use case for communicating between a native driver and the Java layer through the IPC, which sounds brilliant to me personally, but we'll have to wait and see when and if that happens. Any other questions before we? Okay, now we're moving to something that is completely imaginary at this stage, so you can't use it because it's not fully implemented. But it's sort of coming to JC Tools at some point in the near future, when I have time for it and so on and so forth. Proxy channels describe a common sort of use case where you want to run your tasks elsewhere, and you have an interface between the process on one thread and the process that should be running in another thread. So what currently happens is you have a bunch of commands or events that you put in a queue to be handled elsewhere, and your command interface would typically be either runnable, or it would be called handle, or do it, or work, or whatever. So you put bits and pieces of work on a queue. They're all different, but they're all part of some sort of contract between two threads. And what I'm trying to do with the proxy channels is address that by generating a custom transfer media for you, so you don't need to allocate them anymore. And this works on the sort of API level by first you specifying the interface that you want this proxy to have. So you have a few methods, you're throwing in some primitives, you're throwing in some references. Importantly, all your methods should return nothing. They're all async. So you're passing in, you're not getting anything in return. You generate a proxy for your interface. Gets allocated, it's backed by some sort of queuing solution. And on your side, you just call your methods. And they get written into the queue, and you don't need to worry about it. On the consumer side, you say, just consume some method calls. It will also have the sort of batch semantics and so on, similar from the queue. And you pass your own implementation, the synchronous implementation for that interface. So you specify an interface, you implement your own synchronous sort of implementation of those methods, and the transport layer and so on is generated for you without the need for allocating each event when you put it on the queue. Should you use it? No, you can't, because it doesn't actually exist at the moment, but it should be coming in the next few months. I've seen a fair amount of code that fits into this paradigm, and that should make an interesting sort of option for people doing this. And in this case, it's sort of like a queue. I actually write the contents into two distinct buffers, and at the end of that, I have to clear it out. Okay, so the frame only exists for the duration that it's on the queue, similar to how queues work. And once it's gone, it's gone. Once I've handed it to a consumer, it's done. That's it. That's the last Q&A. Any questions? Once, twice? No. Let's go get some coffee. Thank you very much.